We are live, though it takes a moment. Here's somebody, Mr. Jordan, just said hi all. Hey, Ben, how are you today?
It's another Friday.
Deep sigh.
I'm extremely frustrated because I got all super excited about remembering ATLC version 2 or Mark
Right.
2 is probably a better way of putting it because it's not created by the same people. It's a derived work from ATLC, which is a derived work from MDTLC.
So back up and tell us what you're talking about, and also move the window. It's in front of the words ATL2, ATLC2.
ATLC. This
Yeah,
is
see your little solver window? There you go.
yeah, let me just close this actually. That doesn't seem to be wanting to run. Um, oh, and I've got to
So,
mute my YouTube so I don't hear us a minute after what we've said. Anyway,
yes.
ATLC2 is a derived work of ATLC, which stands for Arbitrary Transmission Line Calculator, which is a 2D field solver, and it's just incredibly, ridiculously useful. And it's open source, basically, or free. There's a hat tip to the original author, Dr. David Kirkby, who's a PhD qualified ham, obviously. You can see his call sign there, G8WRB. And I read his papers when he created ATLC. He wrote a Word document that came with it that gave the theory of operation. And he took a very novel approach to calculating transmission line characteristics based on capacitance. So you know, in early college, they gave us this tough question when we're doing beginning circuit analysis classes, and we're learning the matrix algebra that helps you do formal circuit analysis with mesh sort of circuits, mesh analysis we called it, right?
All right.
And so you take a circuit and you maybe have a bunch of different resistor values in series and parts in series and parallel. You just start with simple DC resistances, and then later on in the course you get to the more advanced. You're adding capacitances and inductances with it.
All right.
And then finally, impedances, and you have to do mesh analysis with Norton and Thevenin equivalents, right? Norton and Thevenin equivalence means, for those watching who maybe haven't studied circuit analysis, it just means if you have any voltage source like a battery, it wants to supply a voltage. But batteries are not ideal. They're imperfect and they drain over time. It's just one example. And so there's this notion that the battery also has a resistance in series with it, which can change over time.
Right.
Right? But that voltage source, which is theoretically ideal, an ideal voltage source provides voltage, and it will maintain that voltage no matter what you attach to it. So even if you put a dead short circuit on an ideal voltage source, it's still going to have that voltage. And so one of two things is going to happen. Your short circuit cannot exist, or it must have some resistance, which we know is true because even a piece of wire has resistance.
Right.
Otherwise,
you'd have infinite current flow.
And so otherwise you have infinite current flow. So an ideal voltage source is a fixed voltage and can provide infinite current, but a real voltage source has some series resistance, so that if you load it with whatever else, it's going to respond accordingly. And that voltage source in series with a resistance can be converted to an equivalent current source with a resistance in parallel to the current source. And these are called, I forget which is which, but one is a Norton equivalent circuit, the other is a Thevenin equivalent circuit, based on Thevenin's you know, voltage laws and whatnot. So essentially, an ideal current source can provide a fixed current and infinite voltage swing in order to force that current to come out of it, no matter what. So even if you open circuit an ideal current source, current must still flow. So where does it flow? Well, if it were a truly ideal current source and you open the circuit, you're going to get arcing through air or gas, or you're going to have electrons magically jumping through a vacuum, because that current will flow. It is guaranteed, because it's an ideal current source. But we also know in the real world that doesn't really happen with real current sources. If you create an open circuit, it'll go up to some voltage and then max out. And so a practical current source is an ideal current source in parallel with some sort of impedance, or in our basic circuit analysis class, it was a resistance. And you can convert these things, right? So the interesting nature of all of this is that, they gave us this problem. You have this tub of water, and you have electrodes with a voltage source, and water is partially conductive. It's got some resistance, but how do you model that? Well, you model it by having this huge mesh of resistances.
Okay.
So it's like having, and you could quantize it if you were going to numerically solve it. You could have a very rough model where you have only a few resistances in series and parallel that represent the liquid in the tub, or you could have a more accurate model where you increase the number of resistances in series and parallel, and you basically make a mesh of resistances. It's a grid. It's essentially a grid. And we can do the same thing if you have a theoretical conductor. Just take the cross section of a conductor like a PCB, and you take a cross section. You have a ground plane and you have a microstrip line, and you look at that conductor cross section, and you divide that whole thing up into a mesh, and the field solver can either model it as resistances at DC, or in the case of ATLC, modeling it as capacitances. And that makes sense if you think about it, because the circuit board, the main material in the circuit board is a dielectric.
Dielectric, right.
And its characteristic that we measure it by, or use it with, is the dielectric constant. Well, also called permittivity or decay on a data sheet. And the permittivity is a measure of its capacitance per unit volume, right? And so what ATLC does is it it takes a generic bitmap where different colors in your bitmap represent different materials in the cross section, and then it divides the whole thing up pixel by pixel. It gives you a pixel by pixel mesh, and it calculates, okay, between this conductor and this, we have all these little pixels that represent FR4 in a PCB, and all these ones that represent air. And it creates that mesh of theoretical capacitances in series. So if you take two conductive plates and you have some dielectric material between them, that's a capacitor, right? Everyone knows that's a capacitor. But you can divide up the dielectric into thin chunks, and each of those thin chunks can be modeled as an individual capacitor in series with the capacitor next to it, all the way across. And so that's what ATLC, essentially, I'm oversimplifying it, but that's how ATLC divides the whole cross-sectional view of your transmission line. And it works for cables as well. You can, and this is why it's called arbitrary transmission line calculator, because it's not just for strip lines and microstrips on a PCB. You can make a bitmap of any colors and shapes that would be extruded into a strip line and determine its impedance, its capacitance per unit
Wow.
length,
Okay.
its inductance per unit length, and all of that goes into figuring out. And you can have it solved for different frequencies. So it's just it's really cool bit of open source kit that you can download here from this page. And I was trying to get it to run with some bitmaps I'd used in a presentation I'd done previously on RF and microwave PCB design. But for some reason I couldn't, before we started transmitting to YouTube, I wasn't able to get it to solve anything sort of sensible, but I'll just try and use the default here. So it comes up by default. It uses a bitmap, right? And the bitmap black just means space or vacuum. Red means a copper conductor with normal copper properties. You know, it's got resistivity, it's got I don't know if I don't think ATLC models surface roughness, so that would be something that hopefully the developers would consider adding to that. But red means it's at a positive potential of 1 volt. Blue means it's at a negative potential of 1 volt. And this is a twin line, you know, basic twin lead, like the old antenna ribbons we used to have for free-to-air TV. And the control panel here has some controls for setting up basic round twin leads, square twin leads, a coax, and different materials. And if I click this, it shows you the palette of standard material colors. So red is positive 1 volt copper, green is ground. So wherever you put green in your bitmap, it's ground with the copper conductivity. See, the conductivity could be there.
Right.
This is copper conductivity, 1.7, well, rho is actually resistivity unit, and blue is copper at a negative charge, and there's different conductors and so on, and different resistivities, and light blue is a non-charged conductor that's just floating. So you may want to say, well, what's the impedance of the cross-section of something where there's a piece of metal, but that piece of metal is just a bit of shielding or something that's not actually carrying any of the current for the signal.
Right.
So you can set all that up, and you can specify, you know, what frequency we want to solve at, and then you can choose what fields you want to show. So we can have voltage field lines. We can have equipotential and voltage field lines, which I like to show.
Right.
And then we can go ahead and solve it. So hopefully, you know, typically this didn't take long in the past. So it shows you the status. It is multi-threading as well. You can see over here, you can choose how many CPU threads to use.
Right.
So this is running 12 threads.
And Skype is still working.
Which is amazing. So it's doing a bunch of things in parallel here. And we'll see what it does.
Right.
So the piece that I'm currently missing here, and this is probably something someone's actually done with Eagle and Fusion, you can run ULP scripts, right? And the ULP scripts. So I have my layer stack design in my PCB editor, and I want to define a trace cross-section for a microstrip or strip line, and then take a section of that and have it generate a bitmap in the correct color scheme to open it in ATLC2. You see?
Right.
So this is finished now, and you actually see the field maps are done, and it shows it's actually, if I can zoom in a bit here, you can see it color codes now also the conductors to show skin depth, which is pretty awesome. And so that's a pretty picture. It's nice to have a pretty picture of field lines. Well, I know how electric and magnetic fields work in charged conductors, so I could probably draw this on a piece of grid paper by hand, but that's not the value of it is not the pretty picture, although that's super useful to give you an intuition about different transmission line shapes and how they actually, where the energy is. Energy is between the charged conductors. That's where the energy is densest, but energy goes outside of it as well. And this is why in a printed circuit board, if you have a transmission line microstrip and it goes away from the reference plane, it becomes effectively an antenna.
Antenna, right.
And you get EMI problems, you get radiation. Maybe that's unwanted. Or you'll notice if you're doing something with an ESP32 or similar, RF microcontroller, the antenna that's the squiggly meandering inverted F antenna on the printed circuit board, that will never work if you put ground plane under it. It has to be outside of the ground plane region on your printed circuit board design so that it can radiate, but it has to have the ground plane region nearby at the right place as its reference.
Right.
So you need both, but the strip line part that makes up the antenna radiating element won't radiate if it's right over the ground plane. It's always apart from the ground plane.
Right.
And so so what happens, then we get our results in the control panel, and I really like this. This is a good bit of development. If I stretch the control panel out, it auto scales the text and everything. And let me, went off my screen there. I really like that. I don't know if they used Qt or WX widgets or whatever for I don't know what software they used for the UI in this, but I really like that. I think, I think all software should do it that way. But anyway, so this is telling me this is my capacitance per unit length.
Right.
This is my inductance per unit length and resistance. And it's given me the actual characteristic impedance of this transmission line and its velocity factor.
Right.
And this velocity factor is a little bit less than the speed of light, which would be 1, because this is an ideal transmission line in an ideal vacuum.
Right.
So this is a 251 ohm transmission line. And so you can use this to design a transmission line if you want to design a cable or a twin lead. So I guess what a lot of people use this software for is there's a lot of antenna feed lines for HF, shortwave, VHF, UHF ham rigs, and it's awfully convenient to build a twin lead feed for especially if you're doing HF and VHF horizontal antennas where you have a dipole strung up between two trees or poles. It's usually a twin lead you're going to feed the antenna with, and this allows you to design a properly matched, impedance matched twin lead that's matched to the antenna impedance, which is usually close to between 250 and 300 ohms. The natural impedance of free space and air is almost exactly the same as it is 377 ohms.
Right.
And this is why it's awfully convenient to use twin lead that's 300 ohms, because it's very close already.
It's a compromise, but it's close. Yeah.
And then so you can run from your antenna down to the rig. You can run twin lead at 300, and they're not perfectly matched, but they're close. And then you have a little bit of pi network or inductor capacitor or something like that.
Right.
and a balun that matches your 300 ohm twin lead to your 50 ohm output of your amplifier,
Right.
or whatever you're driving.
Or 75 ohm for TV. Yeah.
Right. So this is ATLC, and it was a delightful little rediscovery today, just as we were chatting, saying, oh, I have no idea what to talk about today. And I'm like,
Right.
well, I am doing more RF PCB design classes coming up soon. I'll have PCB West. I'm not doing the whole RF course. I'm just doing a 2 hour or half day, I forget, workshop on PCB.
Now, is that a virtual event? Can people sign up for that?
I think it's going to be streamed. I think they're going to video and stream it for those who can't travel or can't, for whatever reason. Maybe they whether it's their personal choice or whether it's because they have to quarantine or something. But it is an in-person event this year in October, PCB West, and I will be there doing my addendum to my RF PCB course that I developed over the last couple of years. Just a half day on PCB antennas, primarily focused on ISM band. So these are going to be some antenna theory and some recap of electromagnetics around antennas at the beginning, like kind of the first half. Just this is how antennas work and what the lingo is and how we measure their, like, how do we qualify them? What are their units of measure? And then the last bit's going to be, okay, so let's put this together to what you would see on a printed circuit board for a typical IoT, where you have a squiggly line that people always see as the classic. That's called a meandering inverted F antenna.
Okay,
but we'll start from a more simple set and look at how they work, and sort of build on that. But
now, where can people find out about PCB West other than Google PCB West? Is there like a website or
PCBWest.com?
Okay.
Yeah.
And that's normally you pay to go to these things. Do you think it's paid to also stream?
They have a one-day exhibition hall like a lot of these events, and you don't pay to go to that. And I'll endeavor to be hanging around and talking to people for that as well. For the actual classes, the actual conference, where there's a whole lot of really awesome classes by fantastic teachers, people I really look up to, like Rick Hartley. Those you have to pay to attend.
Right.
And of course, they don't really pay me. I'm delivering a class. I think they might give me a little bit of something, but it wouldn't cover hotel. So anyway.
And who would want to go to a PCB West conference?
I'd recommend it to anyone who wants to design hardware. Seriously, anyone who designs boards, even if you're, it's really targeted at people who design boards all day, every day for a profession. But I'd say even any engineer who designs only a few boards a year should go to PCB West, because PCB West is where you really get to learn how to design boards so that they're manufacturable, economical, really deeply understand things like signal integrity. They also piggyback on PCB West. I don't know if they're doing it again this year, but the training companies that do CID and CID Plus certification also typically bookend, or at least at the beginning, the weekend leading up to PCB West, they'll do classes at the same location. So you can do your CID or CID Plus certification and then attend PCB West. And it's a really good way to do it if you can.
Is there a PCB East?
There is. I've never been to PCB East. It's run by the same It's run by the same company, UP Media Group. I don't think they run it every year like they typically run PCB West every year. I don't think they do PCB East every year. I'd have to look into that because I'm not sure when it is or where it is.
Okay.
I know they did PCB West virtually last year, and that was the only one that they had. As if the whole thing's virtual and people are zooming in, there's no need to have an East or a West. So
Right.
Yeah.
So somebody did notice in the chat channel I have a Commodore 2001 sitting on the counter behind me here. That's amazing they could tell what that was.
Full Metal Fab, gotta love it.
Yeah.
And thanks for joining from Ontario. That's cool. That's cool, eh?
So, yeah. Speaking of which, I will be if you've heard of the Toronto Pet Users Group, TPUG. I'll be taking part in their September 16th virtual meeting. So it'll be half on-site, half virtual meeting. So for you in Canada that are part, or anywhere that's part of TPUG, I'll be seeing you on September 16th.
So Bill, you're also showing something there, which is completely different subject.
And now for something completely different. So, hey, but I do have a question for you. You mentioned on the ATLC modeling that didn't model roughness. I was going to ask, so how do you express roughness as a percentage of surface area versus the non-rough surface? How do you put a number to surface roughness that would work with different software?
It's usually modeled because what surface roughness is if you could zoom right, if you could take a cross section of a part of circuit board and polish it into a micro section, and you can do this. In fact, we could actually probably bring one up in the browser. Let me just Google it real quick, and we'll show it. Copper surface roughness. It's actually the RMS, or root mean squared average, or mean.
Right.
The only correct term for it is the root mean squared. The root of the mean squared of the cross-sectional area of the trace. Or actually not even that. It's called the tooth of the copper. So let me bring this over to my.
Yeah, in optics, there's like the dig and stuff like that. I can't remember the different names for the.
Yeah, so surface roughness, and these are actual scanning electron microscope imagery generated from looking at the copper foils used in PCBs, right? So they do that to get a measure. You could do it in 3D, but it's more convenient in 2D to do it with a microsection like this. And they actually use the microsection under a microscope like this and use measurement tools, the measurement tools on the microscope software to put peak and valley lines, and then they take the RMS of that, and that's what you get in a copper foil data sheet from a PCB materials manufacturer.
Okay.
And then that can be plugged in. So this is exactly what I was saying. These are the RMS variance, right?
Right.
The RMS of the height of the variation, and that is plugged into various formulas used for calculating losses. So if you want to look at many of the papers developed for impedance calculation, they also talk about loss. And it can also be plugged into different simulators that'll just take the RMS and use a nominal sort of formula to calculate loss.
Right.
Or you could they'll model it in a small software model. They'll model it and combine that with the frequency dependent skin depth.
Okay. So I was going to ask then, what causes skin depth? What is skin depth, and why is that like predominant in this stuff?
Well, so skin depth means the higher the frequency of the signal, the thinner, or the thinner the actual conductive area becomes. So you may have a big chunk of copper,
right?
But at super high frequencies, the electrons only wiggle around in the surface of it, that's called the skin, and the skin depth gets thinner and thinner and thinner as you go up in frequency. And so for really, if you're doing high-powered RF boards or microwave boards or sonar, if you're doing LiDAR, if you're doing really high-speed digital, like over 20 gigabits a second, you really need to consider using different copper foils that are specially made with lower surface roughness, and so you get lower losses due to skin depth. It's called the skin effect.
Is skin effect? Go ahead.
You were asking what causes the skin effect,
right? I was going to use the I word. Is it the inductance goes up as you get closer to the center of the conductor?
No, there's a number of different theories that contribute to it. Like
distance
proximity,
traveled.
like proximity effect is one of them, for example. However, the way I think of it is more practical. And it's hard to describe, but I can personally visualize it in my head as a river. What you're dealing with is with signals, the actual energy of the signals transferred in the fields around the space and dielectrics around the conductors. That's where the energy is. The fields and waves are traveling through the spaces. But what happens when you have a moving field and a conductor nearby is that the charge inside the conductor has to move to accommodate the field, and vice versa. If you take charge in a conductor and you move the charge, it's going to create moving fields. Right? So what that means is in the copper there's electrons, and because it's a conductor, the electrons can move around freely. They're able to move throughout the material. And so as a wave of a signal passes by the conductor, the electrons in it are moving.
Jostling around, right?
And that is just like if you have a river and water, or a channel of water, let's say, in a tub, a trough, and a signal's passed by a paddle at one end pulsing it, and a wave moves along the trough and gets to the other end and moves another paddle which detects the signal. Okay. The faster those things move, the water. This is like it's a flawed analogy, but stay with me, okay? Because it effectively amounts to the same thing. The water deep in the trough, the molecules of water deep in the trough can't move as freely as the water molecules at the top. Now, there's mechanical reasons for that in the water, and in the actual water trough, there's weight. We can't really consider it that way in a conductor, but because of you said permittivity, because a conductor also, in the presence of a magnetic field that's changing, it creates eddy currents and other things. And I mentioned proximity effect, right? So this, the net result of all of those things, it means that the electrons deep in the conductor are less subject to the field than the electrons shallow in the conductor.
Right.
And so the electrons on the outer edges can move more freely than the ones deep inside it.
Right.
And it's kind of like the water on the surface of a lake can make waves and move easily, but the water deep in the lake can't hardly move. You can have slow,
I picture it that
currents,
way too. Right.
You can have slow, steady currents, and you could have convection even, but it's very slow because, in the lake analogy, it's because of mechanical forces like weight, the weight of all that additional water on top of it, and so on. But it's kind of similar in a copper conductor. You have it's harder for the forces to get to the electrons deep in the conductor. Is the bottom line.
Right.
And
I picture it that way too. Only I picture it like momentum deep in the conductor is it's harder for it to stop and change direction, charge, energy. But in my mind, I always considered it like, well, near the edge of a conductor, it's got less inductance because it's not surrounded by conductor, whereas the core of the inductor is completely surrounded by the inductor. And to me, it felt like an inductance thing, that there's more inductance, more momentum, more resistance to a change of direction down in the core of the conductor.
Inductance is certainly a big part of it because of eddy currents and things like that.
Right,
so,
but then there's the physical aspects of it too. Then,
and the higher the frequency, and when we say high frequency, we're also talking about a digital signal where you just turn something on and it stays on. It's not about clock speed. It's about the speed of switching.
Right, the rising edge.
If you have a very fast
edge.
Rise time or fall time, there's a lot of high frequency components to that. And if you need to maintain that edge and keep it clean for whatever reasons, maybe it is a clock edge and you have to have a good sampling for other signals. Well, this is where your losses, your impedances, and things like skin effect can really have an impact on high-speed digital designs.
Right.
So you want a nice open eye diagram where your transitions are clear and you've got a very definite 1 and a very definite 0. And you go 2 inches across the printed circuit board, and at the other end you'd measure it and your eyes almost shut, and it's hard, like the chips have a hard time detecting what's a 1, what's a 0, and
right. And also I've heard that in the eye diagrams, what we end up with is edge detectors, and so it's also the rate that it gets to that high or low. There's which contributes to the size of the openness of the eye diagram. But at the end of the day, we've got 2 signals in a differential, and we're detecting those edges. The energy of the edges is what helps propagate. It says, okay, that was the transition, and now we're holding that transition occurred, which keeps the openness of the eye diagram.
Right. You need to hold it. As well, so that
not holding it sucks too, right? So you gotta get there quick and then hold it.
And then when we've talked about this before so many times. Even with the C64 and C128, you had to run that extra wire on the C128 because the hold time
couldn't hold it. Right, reflections were showing up.
Yeah, so you have to hold it so that the clock happens. When the clock happens, it's sampled in a stable 1 or 0. So
right. And that example on the C128 where we added the wire, I suspect that probably the segment was ringing. It probably wasn't just a single reflection. It was probably ringing up and down because in theory there should have still been like 15 nanoseconds for the ringing to die down, which is just forever.
Yeah.
And yet it was still active 15 nanoseconds later.
Right.
So speaking of which, we didn't worry about skin effect in the old days.
Didn't have to.
Didn't have to, because now, we talk about the 8-bit era. I always default to 1 megahertz when I think of the 8-bit era. But again, The real frequency is that radian frequency, as you just were talking about, which is the rise time and fall time. That's what gets into your radios. That's what causes interference. That's cool eye diagrams there. So yeah, in the old days, we didn't troubleshoot for the effects of that. We didn't have to troubleshoot for the effects of it. And if we did, it meant there was a serious problem, such as the wire on the C128. So, yeah. But I did a class with Rob Clark. This class is 10 years old, and I'm not going to know all the parts. Rob and I combined our efforts to talk about how to troubleshoot old 8-bit machines, and I was going to step through that real quick. I don't know the cartridges that Rob talked about as well as Rob did, so I may have to skip some steps here. But let me try and set this up. So in the class, we determined, well, what's your goal for your desired level of test and repair? Do you just want to see it working, or are you after a full restore of it? Are you trying to fix the actual components themselves, or is swapping available? And a lot of people with the C64s these days and stuff, they have to do swaps. And we did that as well in the lab. If my computer didn't work for over 15 minutes, I'm talking like a C128 sitting in front of me, I had a whole fresh set of chips. I'd swap them in. I'd take the 30 seconds to do that, because any minute I spent troubleshooting an already bad chip is a wasted time. So, and sad to say, the chips I took out probably went into the trash. They at least went into a pile of don't uses, right? Unless you're hard up for MMUs or something like that. So, so what's our goal? And here we go. So I was taught by a teacher. I did have an electronics class in high school. After I'd quit, joined the National Guard, come back to school, and suddenly I'm academically inclined enough. They let me take Votech TV repair. And in there, my teacher, Larry Davis from Marion, Indiana, taught me to shut up and use my eyes and look at it, right? Look at it. As a TV repairman, if you spend time troubleshooting for something that you could have seen, you're wasting your money, because we got paid on commission. I got paid $10 per TV set. And if I could see the problem and fix it in 10 minutes, that beat the hour it took to find it. And then you look and the resistor's brown or the wrong colors. And what would happen in the old days is the resistor color codes, the resistors that get so hot, and these typically we used 1/2 watt and 1 watt resistors, that if orange became brown, that's a nonsensical value. Instead of orange, red, you'd see orange, brown, red. You'd go, wait, that's the wrong value. That there is no orange, brown, red, right? And that meant that resistor had gotten warm enough that the color had faded on this center band. So look for anything unusual. And here in this set, I don't expect people to be able to see it, but there is something unusual here, and that is if you look right here,
capacitor.
The capacitor is domed. If it hasn't blown, it's about to. I think there's a little dot of stuff, so it probably has blown here. Yeah, it's actually leaked down the side here a bit. So that's your very first thing with troubleshooting. In my world, is use your eyes. Take that 5-10 minutes to look at everything that's in there. I'll talk a little bit more about troubleshooting. I got my big break as a production engineer, troubleshooting digital weighing instrumentation at a company called Pennsylvania Scale Company. And it turns out about 5 of us old Commodore people came from there. Me being the first guy to leave and go to Commodore. And we used to have cuts and jumpers on these boards. And these were 6502 driven boards, but big boards, analog, digital. And I found that I could sit there and fix half of the units without even turning them on by sitting there staring at every single cut job. And I didn't just look like this. I looked at each one and verified, and often the cut would be on the trace next to the one it was supposed to be. Or the jumper almost went to the right pad, just not quite. So I would get a big leg up on all the other technicians. By 9 o'clock, I'd fixed half my bin by using my eyesight. So visual inspection is real important. Here's another technique then. And I did this by kind of by habit. before I joined the service, before I got radio teletype repair when I was in the service, and one of the things they said talked about was localization. And for me, I know that there's an AC plug and a cord and a switch, but what they taught is, no, localization is figuring out where in this chain right here it's broken, and you localize it. Well, if it's broken around the fuse area, then let's start checking the fuse. We don't need to be checking the light if the circuit stops at the fuse. And so what you can do is either start at the end and work your way back, start at the beginning and work your way forward, or you can do a hop skip method, which is, well, a lot of times it's the fuse, so let me check right behind the fuse before I go further. Or let me make sure the cord's plugged in, and a lot of times it's the cord not plugged in.
Did you try turning it off and on again?
Yeah, right.
But we do this exact method I started out with even in audio as well. You get a signal generator, and you do it in RF. You get a signal generator, and you get a good oscilloscope, and you start at the source, and you trace all the way through the circuit.
Right.
You go, okay, at this point, at this first point, that's my signal. I got my sine wave.
Yeah.
At this next point, it should look more like a bit of a distorted sine wave. Yep, that looks right. Next point, it's going to be clipped on one side. Yep. Next point, and you go through, and at some point you realize you get to the place where no, that signal isn't what I'm seeing there isn't normal. So something just in this region is crapped out, and then that's when you find your blown capacitor or your tantalum capacitor that's failed short. The other one is temperature, and people have this luxury now with thermal cameras because you can.
Right. We used to have heat guns and blankets. That was the only tools we had for troubleshooting heat. Yeah.
And for a little while, some companies would put the whole active board in a bath of Freon.
Right. All right. You're breaking up a little. Yeah, we lost Ben there. So, is he coming back? So, Ben mentioned audio troubleshooting, and one thing I'll say about audio troubleshooting that was an advantage then is that there was a left and a right channel. So, in addition to being able to program through, so Ben, I was just talking about, you talked about audio equipment. One of the advantages to troubleshooting audio equipment, especially without schematics in the old days, was you had a left and a right channel. So you had, a lot of times you had a known good channel to compare it to. So if you go in there and you say, well, that looks a little clipped, but is it clipped or not? Well, you would look at the working channel, and it oftentimes would give you an answer to that.
Yeah.
Now I developed a technique because again, I was a street fixer, right, in the old days. I used to go to Matter Park in Marion, Indiana, with the tackle box of parts. A lot of times just the audio outputs, because people were always shorting their outputs together in their 8-tracks. Remember 8-tracks? They would pop their outputs. So I would use my finger as a test point. And if you put it right on the recording head or right up if you've ever touched those wires up inside where your needle on your record player is, you hear this loud pom. Yeah. Well, guess what? That's a valid test point. One time my boss brought in his stereo, and he was trying to figure out why one channel wasn't working. And at lunch, I was like, well, do you mind if I look at it? And he's like, yeah. He had out the audio test generator. And I just licked my finger and I went, nothing, right? So I back up, and I traced it to where in the old days, you could have the signal come out of the chassis and go right back in, and they had a jumper between two phono plugs. And I just wiggled that and it started working. So I fixed it in less than 2 minutes using just my finger, which you would have thought would have made him happy, but in effect, he kind of pissed him off. Because he had spent his lunch hour looking at it. So, but that's localization.
Yep. Very cool.
Supplies. So power supplies are good. What next? Supplies. So we always start with power supply. Yes, always start with the power supply in my book. Maybe not everybody, but that's what I do. Diagnostic hardware. There's built-in diagnostics, but that assumes that it runs good enough to run the diagnostics. Well, the problem with a processor is almost everything has to work before anything works at all. before it can, one of everything except the RAM has to work for it to fetch its first instruction from ROM. It goes to ROM, and real soon after that, it'll do a stack call, or it'll jump to a location, and that means RAM has to work. So within about 20 cycles of a processor, almost everything has to work. Maybe not the I/O, the input-output devices, the read the keyboard, for example. Everything can work, but you can't read the keyboard. Okay, that's getting down to that device that's broken. But the problem is you got to have a lot working before nothing works at all.
I can't see the whole slide there, by the way.
Yeah, let me pull that up.
That's better. Cover me. You're the one talking.
All right. So
That's better.
Yeah. So again, I'm not going to know all the intricacies of these different ones, but this one was made for the PET, and it swapped in ROM and RAM. Well, guess what? That tends to mean that you can have broken ROM and RAM and still have it work and have it boot up. Now it boots from the cartridge, so you go, oh, hell, the processor works, the reset circuit works, the clock works, I/O works if your keyboard works. So you start to get an idea of what's working, and then from that cartridge you can go in and test the ROM or RAM a lot of times. Other PET tools, I don't know what they are. Here's another PET tool, Diag PET. And for all you PET people, I'm sorry I'm going so fast. I simply don't know these tools. Rob is an expert on these things. Then we got to the Vic20 Diagnostic. External ROM with its own RAM, same idea. You plug it in, and it takes over enough of and what we did in the VICs and the C64s is we would pull certain lines low, and it says, give me that ROM and RAM. That's how cartridges work. They say, give me the ROM, for example. I don't need BASIC swapped in. I need every bit of space I can, so I'm going to use it for the external cartridge, in this case, a diagnostic. And you might as well throw some RAM in there in case it's the RAM that's broken. We use the RAM in the cartridge again to fix the broken RAM, or detect the broken RAM in the insides. Once the diagnostic runs, then you can build little external dongles, for example, to test a keyboard connector or a I/O connector. We loop some of the output back to the input, and if you can toggle the output and read on the input, that means both of those are working. If you don't get that input back, it means one of the two of them most likely is broken, but at least you know now. So we did this in production. When we slapped a 128 board on the test jig, they would plug in, every connector would have some kind of dongle plugged in, so we exercised absolutely as many of the signals as we could.
Now, tell us a bit more about that test jig. Did you guys use bed of nails testing, or how was that back in the day?
We actually didn't. For the C128, we would use bed of nails for the PC board electrical tests sometimes, but that was done overseas, closer to the actual source of the board. In our production, we didn't use a bed of nails. We simply clamped it down, powered it up, and tried to have the diagnostics kick on as much of the circuitry as we could. Okay. So it was basically a dead or no dead detector. Then you would do some swapping, and you would swap the VIC chip and the processor, without even thinking about it. Now, in production, they would be careful about what they swapped so that they weren't throwing away as many chips as I did in R&D. It's a completely different environment where we're trying to reduce our scrap as much as possible. Okay, so this cartridge used what was called Ultimax Mode, and somebody just mentioned Ultimax to me the other day. Ultimax was the predecessor of the Vic20, called the Max Game Machine. Yash Terakur did that. Let's see, somebody's did PC debug, logic analyzer for... Yes, logic analyzers are useful. No, there was no JTAG back then. But Ultimax Mode, it was even... The idea was the computer was even lighter and had less resources than the Vic20, which was a 16K machine. So in Ultimax Mode, when we're in that right mode of combination of these little jumpers down here, called XROM and game, it swapped out the whole ROM and RAM to the external. And sure enough, if you read the book, the Back into the Storm book, which just came out, in there I tell the story about how we got one of the equations wrong for Ultimax mode, and it turns out our own football, aka soccer, was an Ultimax mode cartridge. Thank goodness we found it before we went to production. So Ultimax mode means give me all the RAM, ROM, and it's a great way to fire up a C64 or a C128.
So tell me about that picture there, though. The cartridge card looks like it's either damaged or had a manually cut out slot.
It had a manually cut out slot, but that does look weird. But this is what almost all C64 cartridges look like on the inside.
Yeah,
this is the footprint of a standard, fit the back of the 64 cartridge. Now, Frank Buss is saying, it was Frank that told me about Ultimax mode the other day. Internal RAM below 1000 is still there, which is 4K probably, if I remember right. So there was still some there, but we took the bulk of it, went away because Ultimax mode just didn't have it built in. It relied on, they were putting the cost in the cartridge itself by adding ROM and RAM in the cartridge.
Yeah, and that's an interesting point too, because most of my friends in Australia, all our games were read off a tape, or the one or two lucky kids got the floppy disks.
Got the floppy, yeah.
They were so much faster. But I remember the painful, 30 minutes of waiting here and there for a tape to be read into memory, and then for it to execute.
So
and
I'm going to say
copy our games on those 80s dual tape decks that could do dubbing, and friends would always try high-speed dubbing for their Commodore tapes. I'm like, guys, that's never going to work, and it never did.
Well, I'm going to say something good about Apple. All right, and you're not going to hear me do this very often.
Pause, everyone. This is a rare moment.
Right, because I believe Apple's rewritten a certain amount of history about their own significance, and they're allowed to. They're still around. We aren't. Commodore isn't. So it's inevitable that some of that happens, and some of it is who was first. And in my mind, it was, who was better? Quantity had its own quality, and to me, 27 million or 12 million, however many C64s, 2 years after one of the Apples, was better than the Apple that came out 2 years earlier that just sold 1 million or something. So in my mind, but they did something first, and they did it better than us. And I found this out when I narrated the what was the name of it? The 8-Bit Generation Wars, which if you Google it, I did the narration for Junk Food for that. And that was that our tape drive worked so well in the mind of Chuck Peddle that we didn't need a floppy drive. We simply didn't need it. And he was right. You could put your finger on the tape and slow it down, and it would still work. You could have an off-center capstan, and it would still work. It was a very aggressive tape drive mechanism as far as tape drive mechanisms went.
Yeah.
Well, Apple didn't have a good tape drive mechanism, so they went to floppy 2 years before we did. They simply did. So Apple was first to the floppy. Apple's floppies, I don't remember if I can't imagine they were cheaper than ours, even though ours cost as much as the 64. You spent $200 on a 64 and $200 on a floppy.
That's why none of my friends had one.
Right, it doubled the cost.
Yeah, they all had a C64, and they used the tape drive that came in the box from Kmart with it.
Right, which was, or it cost $40 or $60 or some, way cheaper amount. So, hey, we're at the end of the hour. I should stop here and just save the rest of this for next time.
Yeah. There's a lot more to delve into there.
Be tuned next week when we talk about what it brings to bring up a chip. There we go. And this is what I did to bring up. Let me bring it up higher on the screen. This was part of what I was talking about when I brought up the vacuum fluorescent display version here in the lab. I had to make sure I had a stable clock, a clean reset. I had to check the ROM chip select. So there are things you can do to check the order of your processor booting, and that's part of what this this presentation was about. Again, this was a VCF East presentation 10 years ago, and I'll just use that as a plug for in October. VCF East is going to try a real event. I should be there for that, and I'll be talking about Commodore. I haven't spoken on a Saturday in 10 years. I'll be talking on Saturday as one of the regular presenters. Normally I'm there on Fridays, which is a time when the people with booths have off. So it was always a for the people that are part of VCF event. So I would talk about troubleshooting. I would talk about how to repair monitors and stuff. That's actually when I met Alan Wolke. He was talking about Tektronix and scope probes and all the intricacies of that. So we would do those on Fridays, but this Saturday I'll be there, and I'll be preceding Bill Mensch. So I'll be doing the introduction to Bill Mensch in the 6502. So if you're in the area, try and catch the October show. I noticed I was part of VCF West a couple weeks ago, and they did not stream it live. I thought they would. They did not. My apologies to everybody. I said that they'd be streaming live. A lot of things in the chat room here. What's it say? Data say it, lathe operator or welder. Somebody said I could have been a lathe operator or welder. If I had stayed in Indiana, I would have been a combine repairman. You know, there was no technology, so that actually hits home. I was a TV repairman because that was the highest tech we had in Indiana in the 70s, was a TV. The good news was every house had one. Everybody needed it fixed. We actually fixed them instead of threw them away back then, especially with tubes. You could replace tubes and stuff. So, yeah, let me stop there, and we'll leave that for a reason to come back next week. Somebody just said VCF. VCF, woo! So, all right, how's that for a mouthful real quick?
Whoa, that was a lot. That went by quick.
That's that Bill Hurd adrenaline pulse there that we do.
I love it.
So, Ben, it was great seeing you again.
You too.
We will see everybody here next week, and we'll start off by talking care and feeding of a microprocessor. And, Ben, I really want to see you talk about microwave layout on PC boards like notch filters and stuff. If I can get you to do that at some point, that'd be really cool.
Well, yeah. Okay.
But that's Ben's way of saying we'll see everybody.
We'll see.
Yeah. Ben, great seeing you again. Good seeing everybody. And we'll see you next week.